Hi, we're Team 13 from the Spring 2019 MIT Robotics, Science and Systems course. To complete our final challenge for this class, we chose to implement fast obstacle avoidance on our race car. This task required our robot to navigate through an unmapped obstacle course as quickly as possible without hitting any obstacles along the way. In order to successfully execute our fast obstacle avoidance challenge, our race car needed to do three things. 1. Detect obstacles in real time. 2. Determine what direction to drive in order to avoid these obstacles. And 3. Successfully drive in this direction in the real world while still maintaining a path towards the goal. The first step was obstacle detection. To do this, our race car looks at the data from the LiDAR as it drives. The LiDAR scan collects data about its surroundings in the form of polar coordinates, which represent the distance to the nearest obstacle at any given angle in an angle sweep relative to the robot. The robot only needs to know about close obstacles for this challenge, so we set a look-ahead distance to only consider obstacles within a 1 meter radius of the robot. From here, in order to find each distinct obstacle, we decided that any continuous angle sweep that contained LiDAR data within the look-ahead distance would count as a single obstacle. We found the start and end of the obstacle in terms of its angle relative to the car, and also made sure to note the radial distance the obstacle was located from the car. We then enlarged this obstacle by the width of the car such that the car would not get too close to the obstacle and collide with it. Our car stored this obstacle information so we could use it to determine which direction we should drive. Once we had successfully found all the obstacles in the car's path, our second task was to determine which gap the robot should aim for. To do this, we created a gap selector that considered the list of obstacles as well as the direction to the end of the obstacle course. The gap selector looked at the gaps between the obstacles and checked if the robot could simply drive straight towards the goal. If so, the steering angle was set to the goal direction. Otherwise, the gap selector found the gap that minimized the angle between the new steering angle and the goal direction. Once we had a steering angle that would lead us in the direction of our goal without hitting any obstacles, our third task was to successfully drive the car in the real world along that path. To do this, we implemented a proportional controller that was responsible for adjusting the car's drive angle as quickly as possible without allowing the robot to oscillate and become unstable. With these three components in place, our race car was ready for testing. After a bit of tuning to determine an optimal look-ahead distance, as well as some optimization of our proportional controller, our car was able to successfully navigate several different obstacle courses at reasonably high speeds without any collisions in the final competition. Once again, we're Team 13. Thanks for watching!